Okay, Assalamualaikum Doctor. For our second video presentation is about spectral density function. As my name is Amatul Najah Bintudin and my partner is Ina Azli Azura. So, for the spectral density function, which is known as process of the record, wave record which contain essential information about the nature of ice. So it was shown that in the equation of 2.3 with RSX 0 with the limit 1 over 2 pi 1 over 2 t integration of xt square with the respect to t is the autocorrelation function for tau equal to 0, which is represent the time or average of the wave energy, which is p bar. So to express the average energy in terms of wave frequency omega in radian per second, need to be applied by Parseval theorem. So from the Parseval theorem, the equation use the Fourier transform. So what is the Fourier transform? Fourier transform is the transformation between the time and the frequency domain denoted by xt interchange with the x omega. So to get the equation 2.4, from the Fourier transform will be explained later. So next we need to know about the Fourier transform, which is x omega, which is x omega is a angular frequency equal to the integration of wave record, which is xt multiplied by exponent to the power negative omega t with the respect of dt. So for the inverse, which is terbalikkan untuk mencari to find the xt equal to 1 over 2 pi integration of x omega multiply with the exponent to the power I omega t with the respect of omega. So both of these we call the Fourier transform pair, which and then denoted by xt interchange by with the x omega. So similar to the frequency f in hertz, both the and this frequency in hertz we also call Fourier transform pair in frequency in hertz, which is sf equal to integration xt time with exponent to the power negative I2 omega ft in the respect with t, in respect of t. So from this we can see the difference between the angular frequency and frequency, which is the exponent for which the exponent I omega t, exponent I omega t, which we noted that f equal to omega over 2 pi. So if in the frequency we get the exponent negative 2 pi f as omega equal to 2 pi f. So that is the relationship between the omega and the frequency. Then we move to the to the Fourier, which is equation to get the Fourier transform, which from the statement of Fourier transform xt is equal to x omega. Then we need to prove that x t square in respect of dt equal to 1 over 2 pi integration of x omega square in respect of omega. We need to prove this. So from the Fourier transform, this is Fourier transform. So we need to conjugate the Fourier transform of xt. So we conjugate of x xt equal become x conjugate t equal to 1 over 2 pi integration of x conjugate omega multiply with exponent to the power negative omega t in the respect of omega. So then from the equation, the real equation from xt, we multiply with the conjugate pi. So which means we get the before that from the conjugate is from this where I get the conjugate. So x when x equals to a plus ib, so the conjugate part is x conjugate equal to a minus ib. So then from the equation, so from this equation we get the x integrate xt times with the 1 over 2 pi integration of x conjugate omega exponent negative omega t d omega dt. So then we get so kita keluarkan 1 over 2 pi and then we arrange the equation for x omega and then time with the uh, xt xt times the xt. Then from this equation we get know that this equation uh, is x omega. From the xt times with the exponent I equal t, which is the x omega. So we cancel out this, so we replace with the x omega. So which is equal 1 over 2 pi integrate of x conjugate omega times with x omega d omega. So we get, so from this we we look at the conjugate part, which we can say that x times with x conjugate equal to a square minus I square b square. So I square is imaginary part, so we can equate, so it will equal a square plus b square. So the equation will be, so the equation will be x modulus square. So back to the question, so Parseval theorem. So which this equation will be 1 over 2 integration of x omega modulus x omega square in the with the respect of d omega. So then we have proof that from the xt square we get 1 over 2 pi integration of x omega square d omega. So this is the average energy in terms of phase frequency radian per second. So this is in the angular frequency part. So for the frequency part, uh, xt square dt equal to integration of f square df. So this is for the frequency cycle per second. So then for the next part, I will pass to my friend to explain the to explain. Okay.
Okay, now I will continue to give you some brief explanations about the equations from equation 2.7 until 2.11. So based on the explanation given just now, we can say that after equation 2.6 and 2.4 is added into equation 2.3, means that we will get the equation 2.7 as shown. Then we will get then we will set the limits from t to infinity in order to measure the average waves energy. Okay, next. Okay. This is the equations of spectral density functions of a random waves t xt as follow. From this equation, which is 2.8 and 2.9, and based on the equations of waves energy obtained in 2.7 just now, which we shown just now, Hence, the equations of time average of waves energy can be expressed in the equations 2.10. So we can simplify from the equation 2.8 and 2.9 um, and 2.7. So we will get the equations 2.10. So these equations shows the area under the spectral density functions, represent the average energies of random waves with respect to time. So we often define as 2.11 as shown here. So once we simplify, we'll get the final equation, which is 2.11. So I think with that, we based on our explanation, our brief explanations just now. That's all that we can share with you about the spectral density functions, and we hope that everyone will get something from the inputs that we share just now. So that's all. Thank you.